Now we are going to make a special case where we say that consider the case where x of n is real. Okay, so consider x of n is real valued. Okay, so this is a special case. This is basically a series of special cases, but the special cases are of significant interest to us. So what is the primary property that you have for when you say x of n is real valued? That means x of n is equal to x conjugate of n. Am I right? So then what we say that this automatically implies, what is the discrete time Fourier transform of x of n? It is x e of j omega. What is the discrete time Fourier transform of x conjugate of n? It is x conjugate e of minus j omega. And because these two sequences are equal in the time domain, the corresponding Fourier transforms also have to be equal. So x e of j omega is equal to x conjugate e of minus j omega. Whenever a complex sequence satisfies this property that the value of the sequence is equal to the conjugate with the variable time reversed, then this particular sequence is called conjugate symmetric. So this means the discrete time Fourier transform of a real valued signal is conjugate symmetric. Conjugate symmetric. Okay, very interesting result. It's also a very powerful result. Why is it powerful? Because it gives us some very interesting insights. Because for a real valued signal, we can write down the following. Write down the real valued and imaginary parts of x e of j omega. It will be x r e of j omega plus j times x I e of j omega. Okay. Now conjugate it and replace it with omega with minus omega. That means this is equal to conjugation x r e of j omega, but you have to replace it with omega with minus omega. So x r e power minus j omega minus, because of the conjugation, minus j times x I e power minus j omega. Okay, now in case you are not sure how I got this, take the expression for x of e of j omega. First conjugate it. What will happen? You will get x r e of j omega minus j x I e of j omega. Why am I not conjugating x r? Because it's already the real part. And I am not conjugating x I because that is also real valued. So only the plus j will become minus j. The next step, replace omega with minus omega, you will get the expression on the right. Now compare the real and imaginary parts. Comparing left hand side and right hand side, the real and imaginary parts. Okay, basically the real and imaginary parts on both sides must be the same, imaginary parts. So what this says is x r e of j omega for a real valued signal is equal to x r e of minus j omega. A function that satisfies this property is called an even function. X of n is the same as x of minus n, it's called an even function. So that means the real part of x e of j omega, which is given by x r e of j omega, is an even function. Is an even function. Okay? Very powerful result. Along the same lines, if you compare the imaginary part, it comes with a minus sign, right? If you compare the imaginary part. So minus x I e of minus j omega. So which means that the imaginary part x I e of j omega is an odd function of omega. Is an odd function. So the real part is an even function of omega. This one is an odd function of omega. Okay. So we have proved two results. that we have proved that the real part of basically the first one we already proved that since x of n is equal to x conjugate of n, the Fourier transform is conjugate symmetric. From that we showed that the real part is an even function, the imaginary part is an odd function. Okay. The next two are sort of direct from that particular result. So let us quickly write it down. So this is property number 10. Property number 10, magnitude x e of j omega. What is the magnitude of the discrete time Fourier transform? So this will be equal to the square root of xr e of j omega whole squared, the real part whole squared, plus the imaginary part also whole square root. Right? That is how you define the magnitude of a complex number, real part squared and imaginary part squared. Now notice this is xr of e of j omega is an even function multiplied by an even function. Even multiplying with even, the product will be even. Okay, remember we discussed this way back when we were talking about discrete time sequences, same property holds. This is a odd function multiplying an odd function. Odd times odd is also an even function. Okay, so you are adding two even functions, so therefore this function is also going to be an even function. Okay, so the property number 10 says that the magnitude x of e of j omega is an even function of omega. Even function. So what does this mean? If I am computing the magnitude response of x of n, where x of n is real valued, then it is sufficient for me to calculate the magnitude response on the positive side. Okay, it's from 0 to pi. Okay, magnitude x e of j omega. Why is it enough for me to do that? Because I know that the negative part must also be the same. Right. So this must be the same. So let me use a different color here just to capture that. So I get it because of the fact that it is an even function. Whatever the value is in plus omega will be the same at minus omega. So this is at minus pi. Okay, so I always need to so this is what it means that the magnitude is an even function. So many times when we draw the spectrum of a signal, we draw it symmetric. Why do we draw it symmetric? Because if the original signal x of n was real valued, then the spectrum will be symmetric. Okay, now the property number 11 and then 11, 12, 13, so we can then conclude today's discussion. The phase or the argument of x e of j omega. Okay, we said that this is equal to the inverse tangent or arc tangent of the imaginary part xi e of j omega divided by xr e of j omega. Okay, this is equal to phi x of omega. Phi x of omega. Now I am interested to note phi x of minus omega. Wherever there is omega, I substitute with minus omega. So this is tan inverse xi e of minus j omega divided by xr e of minus j omega. Now xi is an odd function, so it will come with a when you take e of minus omega, it will come out with a minus sign. This will be so this has become minus tan inverse of x of I e of j omega. Because it is an odd function, there is a minus sign, the minus sign comes out. So then you divide by xr of minus j omega, the same as xr of j omega, because it's a even function, and so this becomes minus phi x of omega. So the argument is an odd function. Is an odd function of omega. Odd function of omega. So if I am plotting the argument x e of j omega, okay, So if I say that the argument of the phase of this is like this between 0 and pi, okay, and so this is the argument. I don't need to do the negative side because I can get the negative side pretty much as the negative of that. Okay, so this will be at minus pi. So this is what it means that the magnitude is an even function, the argument is an odd function of omega. So this is a odd function of omega. Odd function of omega. Okay, so let's go back and look at our table. We have proved that the magnitude response is an even function, the phase response is an odd function. Okay. The last two again is sort of very simple. Let me just sort of indicate and then conclude. Property number 12, we are asked to show that what is the Fourier transform of the even part of x of n. Remember, it's x of n is real, so we don't talk about conjugate symmetric, but talk about even part. This is x of n plus x of minus n divided by 2. Okay. This will have the corresponding discrete time Fourier transform for x of n, take the scale factor of 1/2, you will have x e of j omega, and x of minus n. If you go back and look at the properties that we derived, or you can even derive it again. Let me just so that good for us to practice it again and again. Let us look at what we have. Okay, you have x e of j omega equal to summation n equal to minus infinity to infinity x of n e power minus j omega n. Okay. So now if you say I will conjugate this e power j omega, this will come out to be n equal to minus infinity to infinity x. I don't need to conjugate because x of n is real. X of n is real, so I don't conjugate that, I just leave it as x of n. X of n e power, this is a complex quantity, so it becomes plus j omega n. Okay, now I want to substitute m with minus n. So this summation now becomes n equal to minus infinity, m is equal to minus infinity to infinity, x of minus m e power minus j omega m. Okay, what did we do here? We have obtained the discrete time Fourier transform for a real valued sequence x of minus m is given by x conjugate e of j omega. Okay. So use property number 1. Then what you get is this becomes x conjugate of e of j omega. Okay, so I am using number 1 here. What is this? A complex quantity plus its conjugate comes out to be the real part. So this is equal to xr e of j omega, or in other words, the even part of the input sequence x of n has got a discrete time Fourier transform, again for real valued signals. This has got maps to the real part. Okay, and similarly the last of that, the odd part of x of n will map to j times xi e of j omega. Okay, so this again I would like you to make sure you verify both of these. Okay, so we should have ticked off all of these before the next session. So again verify this as well. Okay, so this is what is with this we have a very solid foundation for studying discrete time Fourier transform. What have we done today? We looked at the basic definition. we looked at some examples of how to compute the discrete time Fourier transform. We gave interpretations to the behavior of the LTI system by looking at the magnitude response of the discrete time Fourier transform. We said that this looks like a low pass filter, this looks like a high pass filter. We looked at both of those and we gave interpretations to that. And on top of that, we derived a number of properties which tells us how the duality exists between the time and frequency domain and how we can apply these properties to our advantage. So again, we have just now built up a whole toolkit. From this toolkit, we can then apply to simplify and get the understanding of our based on the discrete time Fourier transform. So once you have these properties well understood, we can then use this to build our understanding of how to use the discrete time Fourier transform as a tool for analysis, also as a tool for design. Okay. So this is what we have. We have built up a good understanding. We will now stop here for this session, but we will pick it up from here, and what we will be studying now are further properties of the discrete time Fourier transform and how we can apply them in the use of digital signal processing. Okay, so that is what is our next step. Again, very interesting topics coming up. We will look at several new concepts in the next session. Look forward to sharing them with you. Thank you.